past 5 days, we have been captivated by one of the most gripping dramas in the history of space exploration.
Tonight, The Sky at Night brings you the inside story of Rosetta's mission to a comet.
It's an historical first for humanity. A spacecraft has landed on the surface of a comet.
The short life of the plucky little lander Philae is already over, but what a life it was. Philae stunned us, sending back data and images from the surface of a very alien world. This landmark image is the first taken on a comet's surface, including the lander's foot resting on a new world.
This mission has always been daring and risky. It has been nerve-shreddingly tense. There have been disappointments and hard decisions. The spacecraft's awkward landing meant that scientists ended up in a desperate race against time as its battery power faded.
They've got it! We've been at the heart of the action, right here at Mission Control, to watch this thrilling story unfold.
Yeah, it's going to be a great day. Yeah.
30 seconds. We'll bring you all the excitement from the last 5 days, why this mission matters, and the first analysis of results from the surface of the comet. The story starts 500 million kilometres away in the depths of space, where the spacecraft Rosetta is in orbit around the comet 67P Churyumov-Gerasimenko.
Meanwhile, on a grey Wednesday morning on Earth, we waited for news.
This is the European Space Operations Centre in Darmstadt, Germany, and behind me is the heart of it all, Mission Control. In there are some people that have had a rather sleepless night keeping an eye on things, and there's some news. The bad news is that one of the critical systems on the Philae lander, the thruster that would have pushed it into the surface of the comet and kept it stable, seems to be malfunctioning. But the team have decided to go for a landing anyway, and the good news is that Rosetta is perfectly on course to make that happen.
Of course, we weren't alone at Mission Control. The world's media was here to share the dramatic story. We're here in the heart of the European Space Agency Press Centre. There's people milling around everywhere. Down here is the press briefing room where they give us the latest information. Upstairs there's a conference room where they relay live links, links like this shown on this screen from Mission Control. Now, there it looks quite calm at the moment, but it's hotting up because in the next few hours they're going to be releasing the lander. And when that happens, I think all hell's going to break loose.
3, 2, 1, top. Décollage.
It's taken 10 years to reach this point. Rosetta was launched in March 2004. Its mission? To track down, catch, and eventually land a small probe on a comet, which is less than 5 kilometres across and travelling at over 50,000 kilometres an hour.
For me, Rosetta's always been the biggest mission. It's got everything. It's got excitement, it's got technological challenges, and it's got fantastic science. And rolling that all in together is why I call it the sexiest mission.
To rendezvous with the comet, Rosetta has flown over 6 billion kilometres, using the gravity of Earth and Mars to propel itself towards its icy destination. By June 2011, it was so far from the sun that its vast solar panels were no longer able to provide power, and it went into hibernation. For 2.5 years, as it closed in on the comet, we heard nothing from Rosetta. Then, in January this year, as it turned back towards the sun, Rosetta's alarm clock sounded and the spaceship made contact with Earth once again. To the relief of the team, the mission was still on course. Between January and August, Rosetta made its final approach to its target, Comet 67P, Churyumov-Gerasimenko. Once it arrived at the comet, Rosetta made a series of complicated maneuvers to get into position to release the Philae lander, the probe that would travel to the surface of the comet.
Earlier, I'd met with the project scientist, Matt Taylor, who explained how they'd chosen Philae's landing site.
This is a scale model of Churyumov-Gerasimenko, our target comet. It's a good indication of the challenge we have in landing, but the key thing you see from this model, you touch it, it's sharp, it's bumpy, it's lumpy, it's not a perfect billiard ball.
And here we are, here's Philae already on the surface.
Yes.
So why did you choose to land here of all places? It seems like there are other places you could have aimed for.
Yeah, I mean, you look at it, it's not a perfect potato, it's a duck shape. We landed on this region through selection of all of the areas we could have, because this was the least worst of all of the selections that we made. We couldn't land in the neck because there's too many shadows. This provided us with the best chance of getting the lander down. It was the least rough. There were less boulders than in some regions. Some people were discussing there was a crater area on the top of the head, which is actually about the size and shape of the landing ellipse. Perfect. It looks like you've already got a natural target area. But immediately we were scrutinizing this and seeing thousands of boulders from 50 meters wide down to meter, 50 centimeters size, scattered all over the place, which is not conducive to a successful landing. So you hedge your bets on a better place, but the least worst, which is what we've gone for.
What about the big flat bit at the bottom of the duck?
Good question. The problem with the flat bit of the duck is it's in shadow for most of the comet rotation. So you get about 3 or 4 hours illumination per comet day, which is not sufficient enough to power the lander. So yes, we may have landed successfully, but we would have destroyed any long-term science.
The issue of how much sunlight the lander could receive was to become key as the mission evolved.
That lander will last for about 2.5 days on battery power that was given to it from the orbiter. After that, it has to recharge with solar power.
And how long will the lander last? In sort of best case?
Best case, nominally it will last until March next year, when it gets to a situation where temperature on the surface is such that some of the internal components just can't cope with it anymore and they'll break down. And that's it. That's the end of the lander mission.
The lander had separated from Rosetta at 8:30 on Wednesday morning, and from that moment, it was entirely reliant on the comet's tiny gravitational pull. It would plummet towards the comet at walking pace, taking 7 hours from release to touchdown. It was a journey fraught with risks. Getting the trajectory right was critical. Even a delay of a few seconds in releasing the lander could have sent Philae spiralling disastrously off course.
After separation, no one knew what happened to Philae. Rosetta had to reposition after dropping the lander, and during that time, no communications were possible for 2 hours, so we had another nervous wait.
The signal from Philae was meant to come in at 11:58, but 5 minutes later, there'd still been nothing. I was waiting with a very nervous project scientist. So we're looking at mission control here.
Yep.
So what screens are you looking at?
We're looking at Stefan. Those guys know what they're looking for, and so it's more looking at whether Andrea's shaking his head, looking happy. It's probably one of the most nervous men in the control room there.
Yeah. Should we be worried yet? It's still time's ticking on a bit.
It's a bit like this. I'll get worried when they start looking worried.
It's just waiting, isn't it?
It's waiting. It's space flight. It's not easy.
By now, the signal was a full 7 minutes late. Matt, this is awful. They've got it! Matt. Okay.
Bloody lander! It's going to be a great day.
That that was incredibly intense because there was a delay in the signal coming back from Rosetta to Earth, and it was a delay of a number of minutes. The control room looked very nervous. My heart actually, I'm sure, skipped a few beats because it's just so tense. And I don't have an instrument on board, but I can't think what the scientists who do would be feeling right now. But it's success. We have the link. We have the link to the Philae, so we're in a good position again. But phew. The world that the Philae lander was travelling to is one of the oldest, most mysterious we have ever visited. Comets are the leftovers from the solar system's formation, icy bodies from the deep frozen zone beyond the planets. We would know very little about them if their orbits weren't sometimes disturbed, so they fly towards the sun. And as they get closer and warmer, they start to change. At the centre of every comet is a frozen nucleus. But as it gets closer to the sun, it begins to thaw. It releases gas and dust, which form a bright head or coma. The closer they come to the sun, the more they heat up, until the final part of the comet is formed, the tail. These can be huge, up to 500 million kilometres long. These fantastic displays in the sky have fascinated people for thousands of years. And today, scientists are still interested in comets because of what they can tell us about the formation of the solar system and even our own origins. Right now, Comet 67P is just on the turning point. It has not yet formed a bright coma and is still some way off forming a tail. But that process has begun, and over the next 18 months, that's one of the fascinating things we'll be able to watch for the first time from a ringside seat.
By early afternoon on that first day, we started to get the first images from the descent towards the comet. So I had to sneak out the hall and show you this. This is the first image from Philae, from the lander, a camera called Shiva, looking back towards the main Rosetta spacecraft. You've got this flare from the sun here, but here's the spacecraft. This is a goodbye image. And I don't know if you can see this, but Rosetta is blurred, and that's because the spacecraft is rotating. It's already swiveling to talk to the lander, and this is going to be one of the iconic images of space exploration. Then came the reverse, an image of the Philae lander from the Rosetta spacecraft, taken just a few seconds after separation. This was the first time that the scientists had seen the lander in over a decade. I got to speak to the camera's principal scientist, Holger Sierks, just after the picture was released. It's an incredible image.
I mean, this is 500 million kilometers away, and taking an image of the lander from 2,000, 2,500 meters distance, just, whoa.
Yeah, and there it is. And did you have trouble finding it? I know you were worried.
No, we didn't have
about
trouble finding it.
there.
It's there. It's just perfect, and it's in perfect configuration
It
for
is.
landing.
And everything works. All the booms are
All
deployed.
the booms are deployed. The landing gear is deployed. Everything is ready for touchdown.
This is one of the great images. You should be very proud of this. Well, good luck. Thank you.
Thanks, we
See you
need it.
later.
Over the following hours, the Rosetta spacecraft watched the Philae lander descend slowly towards the comet's surface. The images coming in of the spacecraft were truly stunning. But spectacular imagery has been one of the characteristics of this mission so far, even before Philae began its descent towards the surface of the comet. Professor Alan Fitzsimmons retraces Rosetta's journey to 67P to show why the images it has taken are considered so astonishing, and to find out how they have helped scientists prepare for the landing.
Well, these images that we've been getting back from the Rosetta spacecraft are absolutely amazing. They're a joy to behold. We've never had such detail from a spacecraft at a comet before. And the reason that we're getting excited as cometary scientists, as well as everybody else that's seeing these wonderful pictures, is because we're used to dealing with much poorer resolution when we just use the telescopes we have on Earth and orbiting above us. But we can use different imaging processing techniques to get probably the best image we've ever had of the comet at this distance from the Earth. And even then we can't see too much detail, But the nucleus of the comet itself, and of course, and Rosetta, are buried right in here.
Back in 2003, when Comet 67P was chosen as a target, we had to guess what it looked like.
This is a simulation of what we expected the comet might look like by analysing images from the Hubble Space Telescope. And you can get some idea that it's possibly irregular, it's kind of flattened, but that was our best estimate of what the comet looks like.
So the Rosetta scientists were expecting a benign-looking world. But the reality was very different.
When we got them, well, it was a big surprise, because suddenly it looked like we didn't have one nucleus, we had two. And wow, what is this? I mean, this was wonderful. Suddenly, this isn't a disappointment, this is fantastically exciting, because we've got to explain, why does it look like this? It almost looks like a binary nucleus. Perhaps two individual smaller comets have, in the dim and distant past, near the start of formation of the solar system, collided and stuck together. And that's still a possible reason for this shape. Another reason may be that the ices and the dust and the gas are all coming out from this region, so that region is shrinking faster than the rest of the comet. We don't know, but that's what Rosetta is here to find out.
It seemed that the comet was getting more mysterious at every turn, throwing up not only questions, but also serious challenges for the mission.
Immediately, your mind also says, how are we going to land on this thing? This is a very irregularly shaped object, and placing a delicate suite of scientific instruments on the surface of this thing is not going to be a simple job.
And as Rosetta got closer, that task became even more daunting.
So here we've got a full frame image of the nucleus of 67P, and it's absolutely stunning. I mean, remember that this is a nucleus that's only 3 miles, less than 5 kilometers long, and we've got so much detail, so much structure on this nucleus, you almost don't know where to begin. Some of the things we did expect, most of the things we did not expect. So we can see that the surface is covered in boulders. Now, those are a big surprise, because we knew again there would be a lot of small particles and so on the surface, but we've got objects there larger than houses. And how can they even survive every time it goes around the sun? Maybe they don't. Maybe they're created every time it goes around the sun, fall back into the surface, and then are destroyed in the next orbit. We're going to have to wait and see. 30 years ago, when I started studying these objects in our solar system, I never dreamt I'd see a real image like this. It's so thrilling, I can't explain. Perhaps, however, the most striking thing about these images is that you look at the amount of detail here and you compare it to what we thought the nucleus might vaguely look like 10 years ago from the images obtained and analysed from Earth, and clearly it shows the worth of sending Rosetta to this comet. The level of understanding we're going to achieve on the nature of comets and how they're put together and how they behave will be mind-blowing.
Back to mission control on landing day, and the tension was mounting. Many of these scientists had spent their entire careers on this project, and they were about to find out whether that hard work would pay off or whether it had all been in vain. These final moments of Philae's descent carried the greatest risk. The closer to the surface, the greater the danger. The lander needed to avoid an array of obstacles, like cliff edges and boulders that would cause Philae to flip over on landing. Finally, it had to stop itself bouncing off. The comet has just 1/10,000th of the gravity that we feel on Earth's surface. It meant that Philae had an effective weight of just 1 gram. And so Philae was equipped with harpoons and ice screws in each foot to help clamp it to the surface.
A mission 25 years in the planning all came down to this moment. The atmosphere in the room was incredible as we waited for the crucial signal. To hear Philae speak to us from the surface of a distant comet.
Well, it's pretty tense in here now. The quiet excitement of earlier is gone, and there's a lot of nervous people. We think the landing may already have happened. The signal could arrive any minute, and all we can do here at Mission Control is sit, wait nervously, and watch for that signal.
It seems quite likely that the Philae has already landed. It's on the comet, but of course it's 500 million kilometres away, and it takes off the order of 25 to 30 minutes for that signal to leave the Rosetta and actually get back to Earth. So its fate is sealed already, but we're just waiting to actually find out what that fate is.
Finally, after over 7 hours of slow descent, the time for the landing arrived and then passed. The room's gone a bit quiet, but nothing yet, and the team in Mission Control look pretty static, so we're still waiting. It was an agonising wait for us, let alone the flight control team.
Everybody is looking at Mission Control, and this is probably one of the most emotional times in their lives, and the world is watching. I'd hate to be in there.
They'll be running through their checks. They'll have a long list of things they need to check before they tell us anything.
Working, and that can make all the difference. It could have touched down but bounced off. Without that thruster to keep it on there, it could be quite critical. So it's great it's touched down, but we've still got a few minutes before we find out if it's really going to get the data.
Initially, it looked like being good news. Right, here we go.
On the tour station, we see the lander sitting on the road.
Yes!
On the road.
We got it! We got it! We got it!
On the road. It's landed. It's docked. We're going to get the data. We're going to see this comet. We're going to analyse this comet. All these instruments now can come online and start analysing it, getting the data, finding out.
And quickly as well.
Yeah.
We've got 2 days, so the lander will probably live now for months, but it's got a battery for 2 days, and all of its individual instruments will scratch and sniff and taste the comet. We've never done this before. I confess, I didn't think it was going to happen. Immediately afterwards, I caught up with a very relieved and elated Matt Taylor.
You were there with us.
How was it? How was it?
Bloody believable. We just made history.
What happened? Did it bounce?
It doesn't look like it did. So
just went.
it looks like it's done the job. The screws are in. They're looking at how much the harpoons have retracted at the moment. So we've got the signature that the harpoons fired, that the screws are deployed. We're waiting for a bit of telemetry. So we're down. We're just working out how down we are.
How important is it to have a lander and the orbiter?
It covers everything now. We're at 100% science. You know, we get that scratch and sniff. We're down at the bottom of the lowest rung of the ladder in terms of where the coma forms, the outer atmosphere of the comet. And now we wait for the images of the panorama if everything's working.
Yeah, so images from the surface.
Yeah,
That's the next week. How long? A few
How
hours.
long is a ball of string? Yeah, I mean, we have to see whether the link is going to uphold, whether there's an angle of the landing. That's one of the important things. If it is on a slope and maybe wobbling around a bit, whether we can keep that link going. But when I left the MCR just then, the link was there. It was wobbling a bit, but we were getting science packets now.
That's amazing. Science back already?
Yeah, there was
half an hour
whole
after?
packets of science coming down at least 10 minutes after the landing. That means it's there, it's measuring, and we're getting stuff back.
And Matt, I'll let you go, but thank you so much. See you later.
Cheers, man.
That early optimism wouldn't last. But at the time, on Wednesday afternoon, it was incredibly exciting. As the science teams got their hands on the data, we were seeing the first close-up images of a comet's surface taken by the lander. At this stage, it's actually looking at the comet as it comes into land. We're quite a way away at this stage, so each one of these pixels is 3 meters, so we can't actually even see the landing site in detail, but you just get the overall feel of the comet.
This is just before touchdown, and we get our first proper look at the surface.
And you can actually see the shadow of the lander on the surface. And the surface is quite interesting. Lots of sort of granulation, and then sort of some much finer powder.
Yeah, I think fine powder's right. I think it looks like you could plonk down into that perfectly safely, and I'm pretty sure that's what happened. Philae gave you a soft landing in this sort of grainy, sandy stuff.
However, as Philae sent back more and more information, it became clear to the flight team that the landing had not been quite so simple.
So what we know is we got the touchdown signal, the landing gear detected it very clearly, and we got radio link after this, including science packet. Very good news.
Yes.
But how did we land? Are we safely there? There may be some issues with the anchoring harpoons. All of this we find out in the next hours, I would say.
Because of various rumours are going around that maybe the harpoons didn't deploy.
That may well be the case. There is some indications that the harpoons didn't fire, which still could mean that the lander is sitting there on the material. But then, of course, we have to think about how we enter the drilling phase.
Yes, because I suppose if we start drilling and we're not securely anchored, then we could actually pull ourselves off the
Exactly,
comet.
so we should avoid
Worst
that.
case scenario.
That would be kind of embarrassing.
It would be.
Indeed.
By early on Wednesday evening, it had become a day of very mixed fortunes. Triumph on the one hand, with data collection already underway, but worries continuing to grow over the exact status of Philae.
We're back in the conference centre now because a press briefing has been called. We think there's a problem, but we're not too sure what it is.
We do know that not everything's gone smoothly since the landing. We think perhaps that the harpoons that were supposed to secure Philae on the surface may not have fired, and if that's true, then anything could be happening.
Not so good news is that the anchoring harpoons apparently did not fire.
With no tether and such feeble gravity, there was little to hold Philae to the surface.
They have lifted off again. We touch down, we're rebouncing very slowly because the landing gear.
So data is confusing, it's complicated, but there seems to have been a bounce. Not certain, but a bounce.
About 2 hours was fluctuation not only in the RF link, but also on the solar generator, which could be interpreted. The lander lifted off and started to turn itself because the flywheel was switched off.
They've got intermittent receiving from the radio link, but also intermittent power coming from the solar panels, which means that sometimes they're indirect, they're looking at the sun, sometimes they're not, which means the lander is definitely unstable, so something's happening.
Scary stuff. Imagine this thing on the comet, sitting there and occasionally bouncing around because it's unstable. It's a terrifyingly scary, unusual position to be in. There's proof that this has never been done before.
What do people say? If it was easy, then it would not be rocket science.
Exactly.
But in this case, that's not the case. Thank you very much, Stefan Mulametz, for this update. Fantastic.
Piecing together the clues in the data, it looked like not only had Philae rebounded, but it was also unstable and turning. Troubling information compounded by the fact that Rosetta had now moved out of contact. Well, we've just finished the long-awaited press conference, and the real challenge is we can't actually get any more data until 8 o'clock tomorrow or 8:30 tomorrow. And so it's a long night looking at the data, trying to find out exactly what has happened to the lander, and then hopefully we'll reconnect tomorrow morning. But it's so I think it's going to be a nail-biting night for a number of scientists. The stakes were high. The mission's success depended on the Philae lander being on the comet's surface so it could conduct its experiments. One of the biggest questions it was hoped that the experiments would answer was about the role comets may have played in the origins of life on Earth.
There are many theories about how life came to exist here on Earth, and some say it didn't begin here at all, but elsewhere, off our planet, and then travelled to Earth on an asteroid or on a comet. This idea is sometimes known as panspermia, and there's no real evidence that it happened. But we do think that comets carry the very basic chemicals that life needs, a class of molecules known as organic compounds. When we talk about organic compounds, we just mean molecules with carbon, like carbon dioxide or methane or even sugars. And without them, none of this remarkable diversity of life could exist. Of course, there's a big jump between simple organic molecules and life, and a crucial step on this journey is to turn these simple molecules into much more complex organic compounds. And this is where comets come in. An experiment at the University of Kent is exploring the remarkable idea that this transformation could have happened as comets hit the Earth. Chemist Zita Martins is testing that theory. So, here we are. What experiment are we going to do?
So we're going to simulate the impact of a comet into a planetary surface. And we have here Mark, who is actually going to pick up a sample and show us.
But you obviously don't have a piece of a comet. It would
No.
be nice.
Well, we put together the ingredients that we know that exist in a comet.
But it looks just like water ice.
Yeah, it is water ice. I mean, we have the proportions of 9 to 1 to 1 of water with methanol, CO2, and then a pinch of ammonia.
Zeta's mixture contains all the important molecules found in comet ice, although without bothering with the carbon that makes a normal comet black. The experiment involves loading the target made up of the comet ingredients into a vacuum chamber, and then using a high-powered gas gun to fire a metal ball into it at 21,000 kilometers per hour, mimicking the collision between a planet and a comet. Analysing the chemical composition of what's left throws up a few surprises.
It's like a big puzzle. We have different pieces, we put all the pieces together and then we can see the big picture. And the big picture is to try to understand which molecules are present in our residue.
Right, so we started with, I like these models, we started with some simple stuff. There's carbon dioxide and ammonia here, but what you found was quite exciting.
Yes, it's interesting to see how an impact had enough energy to break the bonds of very simple molecules, and then the molecules rearrange to generate more complex and important molecules.
The molecules form into more complex compounds known as amino acids.
Amino acids are the building blocks of proteins that have a crucial role in the basic unit of life, the cell. And so even though amino acids are not actual life, they have a fundamental role in life as we know it. Each peak that you can see in this image corresponds to an amino acid
So
in
those
this gun.
peaks are the detections of something in the residue that you were talking about.
So we know that the residue, the analog ice comet, had amino acids present. So we can see glycine, alanine, etc. So very complex molecules.
So you have the impact here, and that's what you've simulated. If I think about a comet, what I think of is the fireball in the sky, the passage of the comet through the atmosphere. Do you have to worry about that? After all, it would have been subjected to high temperatures and all sorts of pressures on its way in.
You have to think about a spaceship with astronauts inside. So the outside is going to get really, really hot, but the inside is cold. Otherwise, the astronauts would die. And definitely we know that's not what happens. And so there is a process called ablation that meteorites and comets, when they enter the Earth's atmosphere, they all suffer ablation. So the outside is very hot, but the inside is cold.
What surprises me about these results is the sheer variety of stuff that you made. You started with a very simple recipe, just a few simple molecules, but you ended up with all sorts of amino acids.
Yeah, a huge variety.
And so that's the key, isn't it? The fact that you can get that sort of complex chemistry triggered by impacts.
Yeah.
So what do you think that means for the history of these chemicals on Earth?
It means that maybe comets had an important role in bringing all the building blocks of life to Earth through an impact.
So comets might have been a trigger that helped get life started here on Earth by creating complex organic compounds in the moment of impact.
Back in Germany, and by Thursday morning, there were many unanswered questions. We knew the lander had successfully reached the surface of the comet, but then it had left again, bouncing along the surface. Had it finally stopped moving? And where had it landed? But most importantly, could it make contact again with the Rosetta spacecraft?
And so, at 8 o'clock that morning, I was ready to doorstep the flight team and find out what they'd learnt overnight and whether they'd located the lander. 30 seconds.
We just come anyway.
Just you. All right. This is good. Where are we?
Good news, good news. We established contact to the lander this morning, exactly when it should have been.
That's good.
It was a little bit interrupted at the beginning. Now we have stable link, we get data, we get science data. We also already got nice pictures now. We still do not know exactly the state, how we are on the surface.
So you don't know whether you're flat or
well, we have a link, so we are obviously not tumbled over, but whether it's on a slope or whether there is some stones which may cause some shadows, this is all what we are analyzing now. But we are having great data, and they're coming down just while I'm talking to you.
Fabulous. That's incredible news. Just very quickly, how did we get here? There was a lot of confusion yesterday about whether there was a landing or a bounce. What was the situation?
The confusion was not just on your side, it was also on our side. Definitely, as we understand it right now, there was a bouncing, even two. There was one major leap, rebouncing, and then another very short one. But now we are on the surface and transmitting data.
Great.
Still not anchored.
Good. Okay, but on the surface, looking at data, we'll let you go. But thank you very much.
Thanks.
Good luck.
From the analysis of the flight data, it seemed it was no ordinary bounce. Due to the weak gravity of the comet, and with nothing to hold it to the surface, the spacecraft rebounded a staggering 1 kilometre back into space. For 2 hours, the comet rotated underneath it, meaning that the lander travelled 1 kilometre across the surface. However, even a weak gravitational pull is hard to resist, and Philae did then slowly return to the surface, where it made one more bounce before finally settling into the shade, where its solar panels were only receiving a fraction of the sunlight needed. Later, these extraordinary images were released, taken from Rosetta, showing the moment of first touchdown. A dark shadow appears, created by dust kicked up as the lander bounced off the surface. While it was encouraging that the lander was on the surface and transmitting data, there were other key questions that needed answering. Where exactly was the lander, and could it be moved to a better position before the batteries ran out in 2 days' time? Inside Mission Control, Flight Director Andrea was doing his best to find the answers.
We don't know yet in which attitude is on the surface. This we are processing
so whether
the images.
It's flat or whether it's tilted.
Correct. We see at least one foot touching the surface of the landing gear, and we are processing the images to exactly know what is going. But this is fresh news. The image was taken an hour ago, and we received it 20 minutes ago. So
it's wonderful you're talking in almost real time.
Yeah, we are almost real time. Yeah.
What happens today? How much do you get data all day? How much longer are we going to be in contact?
No, the
with
visibility window will finish in a couple of hours from now. So after that, we'll have an outage of another several hours, and this is planned. This is absolutely nominal. Now we'll try to understand where the lander is and which attitude it is. That is the most important information we have to derive.
All right, we'll look forward to the images.
Yeah.
Still excited today?
Oh, absolutely, absolutely. Even more than yesterday.
Good.
Now we are the confirmation that we are on the surface of the comet. We can process data from the lander, and it's more than this you cannot have.
A subsequent panoramic image confirmed that the lander was indeed stuck in the shade and appeared to be tilted at quite an angle. While the lander was in this position, it would be a race against time to get as much science as possible from the lander's instruments before it died.
I could understand how much was at stake, because a couple of weeks earlier I'd been to Milton Keynes to meet the team that had built one of the key instruments. This is the Open University, and it may surprise you to learn that they're one of the world leaders in designing and constructing space instruments. From within these walls, they've thrown probes all around the solar system, but I'm interested in Ptolemy on the Philae lander. Ptolemy aims to answer one of the most fundamental questions. Where does all Earth's water come from? It might seem strange to look for the answer on a comet, but it's thought that Earth was not always a blue planet. The early Earth was so hot that any water would have boiled off into space. So it's thought that most of the water we have today must have come from somewhere else. And one theory is it was delivered by comets like 67P. To test this theory, Ptolemy was designed to analyse a sample of ice from the comet's outer layer. The samples would be gathered by Philae's drill, which can dig as much as 20 centimetres below the surface. Ptolemy would then use an instrument called a mass spectrometer to analyse the sample. The instrument's principal investigator is Professor Ian Wright. Ian, this looks like a beautiful piece of equipment. It's a mass spectrometer. But can you tell me how it works?
Well, yes, the sample is loaded into this part here. We then slide it down here and the sample drops down into an oven. And so what we're going to do down there is actually heat the sample in steps. What we want to do is to convert the solid icy material into a gas. different components come off at different temperatures. So it's a very kind of easy way of separating things.
Like water boils at 100 degrees C?
Absolutely.
Okay,
yes, yeah.
and then other things will boil at higher temperatures or lower temperatures?
Absolutely.
The gases then get ionised or positively charged. And as they pass through a magnetic field, particles of different masses end up in different parts of the detector.
Then we detect the amounts of each of those, and from that we build up a mass spectrum, and that's what a mass spectrometer does.
I see, a distribution of sort of weights or masses?
Absolutely. And that tells us what the actual substance is.
But as well as telling us what a specific substance is, the mass spectrometer can also tell the difference between different forms of the same substance. And crucially, it can tell the difference between two naturally occurring forms or species of water: ordinary water and heavy water. So one of the things that we're interested in is a sort of water like we use every day and heavy water.
Absolutely, yeah.
And they have a heavy water is heavier.
And so because it has a different mass, you can detect how much of the two species are there by using a mass spectrometer. And so that's what we're going to try and do on the comet.
Heavy water is very rare. In Earth's oceans, it makes up just 1 part in 6,420. The plan is to use a mass spectrometer to measure the ratio of heavy water on Comet 67P. If it's similar to the ratio we find on Earth, it may be an indication that Earth's water was delivered by comets. But it's not a simple measurement to make. So it's fascinating the way it works, but I hate to mention it, it's huge. I can't see how you can get something like this into space.
It's a great shame we can't take this into space. It simply is too large. But I can show you how we actually did it. And if we come over here, this is a mass spectrometer.
That's amazing. But I think this is the beauty of space science. You can take something like that and turn it into this, and it does a similar job. That's miniaturization at its best. Yep. This tiny instrument may provide crucial information about the origins of Earth's water. Getting this far has been a long journey for Ian and his colleagues.
For us, it's been a marathon, but it's a different kind of emotion. You know, it's the end of a really long, hard slog. So I don't know, are we excited?
Yes, I'm certainly excited. I mean, I recall putting the thing together and then delivering it off.
So in the clean room?
Yeah. So it was...
working on that scale?
Exactly, yeah. And I remember that like yesterday, but really it was 11, 12 years ago. I mean, I've had children since then, but like now looking back at it, thinking like, yeah, this is it now. I mean, all of our, certainly all of my working life is going to come to... Is it going to work?
Yes.
Yeah. So far, everything has gone right, and there's been lots of chances for things to go wrong.
Yes.
And so far, it's looking really, really encouraging, I think. So.
But now that Philae was on the comet, I wanted to find the team at the Lander Control Centre in Cologne. I was keen to see if the experiment was working and how they were adjusting to the reality of the lander's uncertain position.
The priority at the moment is to do several operations where we're monitoring the day-night cycle, how the water content and carbon dioxide changes. And then we're hoping to be able to use one of the ovens to get more detailed analysis, but we're waiting to see for that.
Okay, lovely. Because I suppose one of the biggest impacts is on battery life available. Can you do any predictions about sort of the your power usage? And are you focusing on certain tests?
We've done tests in the lab. We've got power profiles, so we can predict quite accurately, and it's to use the power available to the best advantage now.
We've brought a spacecraft simulator with us and also an instrument simulator. So what we're doing now is we originally had the plans, and obviously that's kind of been ripped up a little bit now. So we're now trying to rewrite them, and we're actually testing them as we go on our simulator and then passing them over to the lander.
Because you had a drill on board, you were going to dig into the surface. I guess that's not possible at the moment.
There's talk of possibly trying to use that in a couple of days' time, but at the moment we're not really sure whether that's going to pan out or not.
So get the safe science first, then stop doing the mechanical.
Yes, exactly. Our core science was to look at the subsurface material from the comet. So if the drill's not used, it's going to have a knock-on to our core science. But what we're doing at the moment, we're going through a stepwise approach, and we're actually going for the easier science. We're sniffing and we're sampling the coma at the surface. So.
Right, well, good luck with it all, and I'm looking forward to seeing the data.
Yeah, thanks a lot. Cheers, thank you.
It was now Thursday afternoon, and with every minute that passed, Philae's battery was slowly running out. Despite this, the control centre was buzzing. All of the new information coming from the lander was revealing new insights into the character of the comet. Stefano Mattola is the lead scientist for one of the lander's cameras.
We do have dust, we do have ice, but we cannot easily distinguish them. From the orbiter, for example, we see that the ice is sublimating and dust is flying around. Some dust particles from millimeter size to centimeter size are captured in orbit, and we see them coming from the surface, and they get put in orbit.
So because here is actually covered with dust, so it looks as if the dust is quite active on the surface.
Exactly, yeah. We see that there is some transport for the dust, so there is some weather on the surface,
which I wouldn't have expected.
Exactly, yeah. I mean, the comet is a very active beast.
In many ways, the mission was proving a great success. But by Thursday evening, with only hours of battery life left, a crisis meeting was called to decide if anything could be done to move the lander to a position where its solar panels would be better illuminated.
In that meeting room behind us, the instrument teams are gathered together to convene a meeting. They're investigating whether they can use some means to move the lander. The key is to get more sunlight reaching those solar panels.
It sounds like a great idea, and it might even let them drill into the surface. But the problem is that trying to do that might topple the lander entirely or break what's there. That lot have to decide whether to take an enormous risk now or make do with what they can get in its current position. The next morning, Friday, we had our answer. Last night, the team decided to throw caution to the wind and hang the risks. They instructed the lander to deploy all of its instruments, regardless of the chance that that could topple Philae over. One of those instruments was the Mupus hammer, designed to bash through the crust of the comet and reveal the subsurface for analysis. It hadn't been used before, for fear that it could tip the whole lander over. But with time running out, the hammer was deployed, and it made an extraordinary discovery. The surface of the comet was much harder than had previously been thought. So hard, in fact, that it broke the hammer, which might explain why the Philae lander had bounced so high. Throughout the rest of Friday, the full suite of instruments were deployed in a desperate attempt to maximize the collection of data. And plans were laid for a last-ditch attempt to rotate the lander to catch a little more sunlight. Throughout the day, instruments sent back a wealth of scientific data that will take months and years to analyse. And within that data, there should be the answer to one key remaining question. Where exactly is the Philae lander? It seems crazy that we don't know yet where the lander is, but it's actually a difficult problem. We know that Philae is somewhere on the head of the comet, but this is a very large area to search by eye for something that maybe will only be a couple of pixels in the images. So we have to use a different experiment. And what the team have been doing is relying on an experiment called CONSERT. Now, CONSERT was designed to send signals between Philae and Rosetta, which is safely in orbit about the comet. And they were supposed to exchange signals when Rosetta was on the opposite side of the comet. Those radio waves would then travel through the comet and tell us about its internal structure and density. And they have been doing that, but they've also been using CONSERT in a different way. So if we draw a nice representation of the comet there, instead of observing when Rosetta's down here, what they've been doing is observing with Rosetta up here. And because we know exactly where Rosetta is, that gives you a distance to the lander. They can measure the distance between the two. And so if this is the distance here, then we know that the lander is somewhere on this arc. That's good, but what's even better, and the team are trying to do this now, is if you have a second observation with Rosetta over here, you get a different distance and a different arc. And then the point where the two cross is the point where we'll find Philae. The X marks the spot. As Friday ended, the scientists could only watch helplessly as Philae's battery power finally drained away. And on Saturday, I caught up with Andrea for a final update. Andrea, good morning.
Good morning.
How's the lander?
Well, the lander basically ran out of energy from its batteries last night. We had a successful last contact, so we have downloaded all the data that it produced these days, and as more or less at the time it was predicted, we saw the batteries running out, the voltage was dropping, the computer switched off 2 or 3 times, restarted, started transmitting a few data. We saw it was in standby, but then it went to sleep. And now it's extremely unlikely. We don't expect to regain contact in the short term. It could be in a longer term, then maybe there's enough energy received from the solar rays to recharge the batteries, temperature are high enough, but we definitely don't expect contact.
And I know you were going to try to rotate the lander. Did that happen?
Yeah, we had the confirmation in telemetry that the lander was lifted and rotated. Exactly in which position it was finally set is not fully analyzed yet, but definitely the operation was successful. So let's see whether it brings anything in the coming months.
So that is it. The lander isn't completely dead, but it is sleeping. It may never wake up again, but even if that is the last we hear from it, for me, the mission has been a triumph for science and for human endeavour.
For the people involved, it's been a journey almost as epic as that undertaken by the spacecraft. At the end of the week, we caught up with 2 of the key players to reflect on an amazing few days for space exploration. And they revealed that the whole landing operation was nearly abandoned before it began.
Well before separation, 12 hours before separation, my shift was finishing, and Philae was not in perfect condition. So I went home or went to the hotel, and I thought, well, maybe we don't separate tomorrow morning. Inside I was positive, but the status was no-go for separation. So this was very worrying.
We were discussing what's going to happen now we're no-go. So we had that kind of discussion, but we were running tests. And then within 4 hours, I get a beep on the phone from Fred Jansen saying, we're go. And then I sat up in bed. I thought, right, I'll try and go back to sleep. And I was just laying there going, I'm going to the MCR.
But it was that tight?
That was, yeah, it was basically over, you went from one, what are we going to do? What are we going to do? But we know what's going to happen. It was going to be another cycle, another orbit then. But there is that whole thing. But look at how the expectation on everyone, all the teams, everyone's lined up. You guys are here. I mean, if we turn up and go, well, we've got to wait.
Sorry, guys.
Yeah.
But it did go. And then we had that incredible moment of elation and confusion about the landing.
It was you that was standing just behind us when we were all waiting for that confirmation of landing. But what were you looking for? You were looking for the signal from the lander, is that?
The telemetry of Philae for us was not so straightforward and immediate to detect touchdown. In reality, when we realized that something had happened, was at least a minute after Philae had really touched down the surface. And then for a long while, we thought that Philae was somehow on the surface, maybe moving, but we hadn't realized that it was really flying again.
Yeah, what told you that it was flying? What was the sudden realization that it was back up in the air?
Well, we started speculating, definitely. Yeah. Some of the colleagues say, listen, if we have this link that is continuously variable, but then we started, the only thing it can be that is changing his attitude. It cannot be rolling on the surface, tumbling on the surface, otherwise we wouldn't have such a stable link, we wouldn't be doing operations. So the only option was bouncing on the surface. Then when they told us that the anchoring system hadn't worked properly, then it was pretty obvious. And a couple of hours later, they confirmed that the instruments were recording that Philae was still spinning, so it was rotating. And they couldn't do it only in the air.
So now we are in the main science phase. We've done all the operational. Well, there's still a lot of operations to do. We have to stay close to this comet. We hope to stay in a bound orbit gravitationally for the next couple of months. We have perihelion next year when the comet's its most active, and that's going to be
because of the heat of the sun.
Yeah, basically, and it's going to be throwing hundreds of kilos of stuff off, and we get to watch all of this go on. And then it starts moving away from the sun, and so we see everything. Yeah, we see it all coming down again, and we'll get to compare what we see now through that time period and see how it evolves, changing mass, changing features on the surface, and yeah, it's all there now. So yeah,
exciting times ahead.
Exactly, and it's absolutely overwhelming. It really is that it's there. I don't think I've realised what we've done properly. I don't know that it's there yet. It has not sunk in, but it probably will. Maybe on the plane tonight, going home. My poor wife and family are going to have to put up with a dribbling wreck for the weekend.
Yes. Just observing it, I've cried, I've cheered. So for you, I mean, there's been highs and lows. What was your high?
I have to say, well, just being here, being able to talk to you about lander science. I mean, we couldn't dream the fact that it's skipping across the comet as well. That's it. For me, this is the high.
In the past weeks, I was always comparing this when I was asked, well, this is something similar to the moon landing. And inside myself, I say, well, maybe you're exaggerating. Well, now I realize that I think I was not exaggerating at all. The moment I will remember for sure forever is yesterday morning, the day after touchdown, when we were here, no press, no pressure, no family members, nobody around us. We were 4 or 5 people in the control room waiting for Philae signal, and Philae signal came spot on the second. This was really a strange feeling because you think of this machinery that has survived the night, survived tumbling on a comet at 500 million kilometers away, and the moment it was predicted to send data came. This was so deep into my heart that I will always carry this forever.
Andrea, thank you very much.
You're welcome. Thanks to you. Mission done.
Yeah, absolutely. For me, the events of the last few days remind us that we're at our best when we search for new knowledge and when we push at the boundaries of what can be achieved.
The commitment and dedication of a huge team of scientists and engineers led to a world first, landing on the surface of a distant comet.
And so, the life of Philae is over, at least for now. But no one here, and none of the scientists involved in this extraordinary mission, will feel anything but an immense sense of pride. Philae sent back plenty of data, enough to keep us all busy for years to come.
But that's not all. Rosetta, the main spacecraft, will continue orbiting the comet, and they'll both travel towards the sun, so there's much more to see. But for me, there's been an amazing sense of inspiration at this scientific endeavour, and I think it will inspire many generations to come.
One final thought. Astronomers in Chile have just taken this picture of a tiny portion of the night sky. The smudge in the centre of the frame is our comet 67P racing through space with its 2 companions, Rosetta and Philae, the now sleeping lander. In a very real sense, a bit of all of us is up there with them.
We leave you with the sounds generated by one of Rosetta's instruments, recording fluctuations in 67P's magnetic field. The sounds of a comet.